Suppose you have two masses that are connected by a light string and running over a light pulley. One mass is on a frictionless inclined plane. So let's draw frictionless inclined plane. And here is a pulley. One mass is on the inclined plane. Let's call it mass 1. And it is connected with a light string to another mass that is suspended freely on the other side. Okay, here's the situation. It's given to us that mass 1 is 5 kilogram, mass 2 is 1.5 kilograms, and the angle of the incline theta is 20 degrees. So when you let the system move, the system will start accelerating. It's really hard to know which direction it's going to go. We just can only guess. It can either, the mass 1 either can go up the incline or down the incline. So I'm going to guess that the mass 1 is going down the incline. So I'm going to say that acceleration is, it's an assumption, okay? So acceleration is going this way. So our goal is to find the acceleration. Now you could ask, what if I guess that acceleration goes up the incline? Well, you could do that. That's not a big deal. So when you choose the acceleration goes up the incline and then you solve the problem and then you get the acceleration equals negative number, that means your initial assumption was not correct. So that means your acceleration was not going up the incline, but it was going down the incline, or vice versa. So for now, my reasoning why I am guessing that the acceleration is going downwards, it's a guess. Because the incline is frictionless, I am thinking that it will not be, there would be no resistance for M1 to slide down because M1 is larger in mass than M2. So that's why I'm guessing that way. But it could be opposite, you know. Now, the next thing you want to do in reasoning is that thinking, what causes this acceleration? Why is the system of the M1 and M2 blocks are accelerating? Well, obviously, it's due to the forces that act on them. And so what do we know about the forces and acceleration relationship? We know one simple thing, Newton's second law, that sum of the forces equals ma. That is a Newton's second law. It seems like this would be very appropriate law to use. Now, let's understand one more thing. Because the problem tells us that the pulley is frictionless and we neglect it, we are going to we can freely say that the acceleration that the M1 is moving and acceleration M2 is moving is the same, but the directions are different. Acceleration for M1 is going down the incline, acceleration for M2 going upward. So that means we have two objects, and we can use both objects and apply Newton's second law for both objects. That's why we're gonna start with the object 1, mass 1, and see what are the forces that act on it. So first of all, M1 has its weight. Okay, so force weight is always there, and it is on a surface. Therefore, there should be a normal force And then there is a rope, a string, so there is a tension in the string. Now let's draw free body diagram, which is we put the M1 here as a particle, and then all the forces originating from the particle. So here's a M1G. Here's the normal force, and here's the tension. Okay, when you do free body diagrams, it's always recommended that you do the coordinate system right away. In my previous videos, I mentioned that when you have an inclined plane, it's more convenient to use tilted axis. So you make your x-axis parallel to the incline, which means your x-axis will just go through this plane, okay, and then y should be perpendicular to it. So I'm drawing it on the picture so you can see, but we don't want to make the picture to look too crowded. I'm gonna do that on my free body diagram. So I'm gonna choose positive x going to the positive x going up, negative x. You know, because it is convenient to use the motion direction to be positive. I'm going to use positive x going downwards, negative x going upwards. And then a perpendicular line will be my, I'm going to keep positive y going up and negative y going down. Okay, now let's write Newton's second law for this case. That would be sum of the forces, okay, equals mass 1 times acceleration. And let's make it component form. Sum of the forces by x should equal m1ax. Sum of the forces by y equals m1ay. So this is a substitute for this first equation we had. Now, let's identify all the forces on the x-axis. Here's one thing, M1G needs to be resolved into components. Let's go ahead and do the resolving. If we take the perpendicular to the y-axis, we will have M1G y component going downwards, and then M1G x component going to the positive x component. Now, we know that this angle is the same as the incline angle, the angle for the incline. So I can immediately write down that M1G y component equals M1G cosine theta, and M1G x component equals M1G sine theta. Going back to the Newton's second law, since we resolved M1G into components, we can take this off and then write for the sum of the forces by x equals, we have a M1Gx as a positive, so it would be M1Gx. tension going to the negative x minus tension equals, now remember, we always need to put our acceleration on our free body diagram. Acceleration is to the positive direction, therefore we can write this equals m1a. It's positive. Now sum of the forces by y. We have a normal force that is going upwards minus m1g. m1gy goes downwards equals, well, let's see, there is no motion on a y-axis, so there is no acceleration. We say that acceleration on the y-axis is actually 0. Therefore, my equation becomes 0 in here. So let's do a little bit more simplification by plugging it m1gx and m1gy into my equation. This will be m1g, for x I put the sine theta, minus tension equals m1a. I don't even need to write this second equation for the y component because acceleration is not involved in there, so I just don't need that equation. But in my equation that I have, let's call it 1, I can't solve for a because I don't know what's the tension. So I need to find the tension. I would be able to solve it. Now let's keep this this equation aside. Now we need to find the tension, and the tension could be found from the second object that we have, M2. Now let's see what are the forces acting on this second. Second object has its weight downwards, and there is this rope that pulls it, tension. It's the same tension because it's the same string. I keep saying rope, but it's a string. So as long as the pulley is frictionless and the string is the same, the tension is the same. So later we will see when we start not neglecting the pulley's role in the system's motion, then the tension will not be the same. So, but for now, for now, just forget about it. Just the same rope, pulley is neglected, pulley's motion is neglected, and the tension should be the same. Now we're gonna do a free body diagram for the second object, M2, which is, we put the block as a particle, and we have a M2G downwards, and we have tension going upwards, and we have an acceleration going upwards. Also, as I said earlier, let's put x and y axis. So this is positive y, negative y, and then x is not important because we don't have anything. So there is one important thing that you want to notice, that coordinate system for each object is different. Now, apply Newton's second law for this object. We have sum of the forces by y equals ma y. Sum of the forces by x equals ma x. This is our Newton's second law. There are no forces on the x-axis, so there's and no acceleration on the x-axis. The second equation is inappropriate here. So the first one with the y component, I started with the y. I should have started with the x, but I kind of saw ahead, and in my mind, I knew that the x component doesn't exist here. Anyways, let's move on and write all the forces. We have a tension to be positive, minus m2g is the weight of the object, m2g downwards, equals m2a. Don't forget, this is m2. And a is going to the positive y direction, so that's why it's positive. So from here, I can say tension equals m2a plus m2g. Now, let's call this as the second equation, and using the second equation, plugging it into my first equation, I can write, so the first equation, I can rewrite m1g sine theta minus, instead of tension, I'm going to put m2g, m2a plus m2g, and then equals m1a. Okay, now I have an equation that everything is known but the a. So we got to solve for a. Okay, so let's do a little bit manipulation of this equation, m1g sine theta. Well, physics ended when we finished writing Newton's second law. Now it's the math part. m1g sine theta minus m2a minus m2g equals m1a. So let's collect the like terms together. I want to bring m2a to the right. I will get m1g sine theta minus m2g equals m1a plus m2a. Let's switch the places, right and left sides of the equation, and factor the a out. I have a m1 plus m2 equals m1 sine theta. I'm factoring the g out, minus m2. From here, I can find acceleration equals m1 sine theta minus m2 divided by m1 plus m2 times g. All I need to do, plug in the numbers. Acceleration equals m1 was 5 kilograms times sine 20 degrees minus m2 was 1.5 kilograms divided by 5 kilograms plus 1.5 kilograms. And of course, I forgot to put the 9.8 meters per second square, and plug it in into your calculator. You will get this equals 0.32 meters per second squared. So this would be my answer. As you can see, I got a positive value for my acceleration, which means my guess was correct. The system will move to the left. Now, the problem is not asking, but you could totally find the tension in this in the string. How would you do that? Just use the second equation that we have found from the second block, plug in the acceleration, and find what is the tension in there. Thanks for watching. Stay tuned for more to come.